All right, we're going to continue on with Comedy Night. Our next comic, this is pretty exciting, guys. He's been performing at Stilicum for 3 years now. You've seen him on Name That Tune, rap battles, and he's actually the star of Math Think. So let's all just put our hands together for Mr. French. Come on out here.
Hey everybody, how you guys doing tonight? Yeah, nice crowd, good to see you, huh? Yeah, I'm gonna be telling a few jokes today, and hopefully we get a few laughs here and there. You know, there's a lot of things going on in the news lately. You guys been reading a lot of the news lately? You know, I read an article just the other day. You'll never believe this. You ready for this? You guys read this in the news? They put a bunch of the best male calligraphers on a boat. You guys hear about this? You guys read this? Yeah, they got a bunch of the best male calligraphers onto a boat. Great penmanship. Hey, you guys read about this in the news the other day? There was a vegetarian and a butcher. And they decided to set up a conference to talk about their ideals when it comes to food. A vegetarian and a butcher set up a conference to talk about their philosophy on food. And it turns out they didn't meet. Hey, you folks hear about this? World-famous archaeologist Dr. Jones fell over and hit a piece of furniture, but it didn't break. You guys hear about this? All over the news. You guys hear about this? Yeah, world-famous archaeologist Dr. Jones hit a piece of furniture, but it didn't break. Yeah, I guess you could say it's indestructible. Indestructible. Oh hi, Mr. French, your AP Stats teacher. I'm just here doing some comedy. Let's go ahead and do some Chapter 6. Welcome back to Math Think. Hey, all you math thinkers out there, thanks for joining us. This is 6.2 Day 3. We're going to be talking about transforming random variables. Some of this is going to look very familiar. It turns out a lot of these ideas we saw in the past in Chapter 2 when we talked about normal distributions and what happens to things when we transform data. So we're going to talk about transforming random variables today. That is essentially our main goal. So we have one goal for this quick lesson. We want to be able to describe the effects of transforming a random variable by adding or subtracting a constant and multiplying or dividing by a constant. Let's go ahead and get into it. So we're going to start with the context of tourist company, and it's called Pete's Jeep Tours. Pete's Jeep Tours. Peter is a Jeep tour. Pete's Jeep Tours offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. We are going to define the variable x as the number of passengers on a randomly selected day. Number of passengers on a randomly selected day. This is how it is distributed. We have passengers and we have probability. I'm going to call passengers xi, that just means each observation, and then we're going to have probability. I'll call that pi. This is going to be our probability distribution. We're going to see how the random variable x is distributed So we call this a random variable because this variable represents a number generated by some sort of random process. The passenger numbers go from 2 to 6, 2, 3, 4, 5, up to 6. Now it's not uniformly distributed. That kind of makes sense for a tour excursion. So it looks like the probability that he gets 2 passengers based on previous data is 15%. And then we have 25% for 3, and then the most popular, the most expected amount looks like here. So the highest probability is having 4 passengers on a tour, and there's a 20% chance for 5 passengers and a 5% chance for 6. And that kind of makes sense. Like if 6 is the max, you probably aren't going to get the max amount of people all the time. So it's the lowest probability. There's about a 35% chance that you'd have like 2 couples, maybe. That's why 4 is the highest. We could also make a little histogram of this distribution as well. So we can make a little histogram of this distribution. So I have my number of passengers clearly labeled here with the context, and I have my probability. And I've labeled some probabilities up to 35%. So I can go ahead and make this really quick. Well, 0, you aren't going to give a tour with 0 people or 1 person, that'd be awkward. So 2 people, it looks like, goes up to 15%. And then 3 is 25%. Oops. Oh, my bars are really gross. Sorry about that. And then 35%. And 5 is 20%, and 6 is 5%. Apologies for my bars, they should all be the same, but I'm doing this by hand. We're gonna look at an example here on Desmos, because we're gonna be looking at some animations here in a moment. Okay, cool. So this is the probability distribution. Remember, there's 2 things to consider for legitimate probability distributions. A legit probability distribution, these all need to be probabilities. The probabilities need to be from 0 to 1, and that's true. They all do need to add up to 1, and these do add up to 100%. So that's great. Before we continue, let's do a few things. I would like to find the expected value of this random variable. How many passengers should we expect on average in the long run? So we are going to find the expected value of this random variable x. Remember that expected value is like a weighted average. So what you do is you take each outcome, so an outcome of 2, and you multiply it by its probability. Then you add that to the next one. So the next outcome is 3, and you times that by its probability. And you do this for all of them. This is a weighted average. So essentially, I don't want 6 to hold as much, like an even amount of weight, because 6 doesn't happen that often. So it's being multiplied by 0.05. That's gonna kind of decrease its weight. The highest weight here is gonna be 4. So it's gonna kind of hold its own the most. If you were to calculate this expected value, you would get 3.75. Let's go ahead and interpret that expected value. So this is our expected value. It's 3.75 passengers. Never round the expected value. This is an average. Expected value is an average of this distribution, 3.75. Take a look. 3.75 is around here. It's the average of this distribution. So so after many, many trips, the average number of passengers will be about 3.75. So this is a long run average. If Pete were to do many tours on average, if we were to average out all the tours, so on one day he got 2, on the next day he got 2, and the next day he got 4, and then 5, and then 5, and then 4, and then 5, and then 3, and then 6. If you were to average out all of the number of passengers throughout in the long term, the average amount of passengers will be 3.75. Let's calculate the variance as well. So the variance is a little bit different. It's from the previous video. So the variance is a little bit different. What you do is you take each observation, so 2, minus the expected value, which we found to be 3.75. You take that distance from the expected value and you square it, and then you weight it by its probability. And you add the next one. So we do 3 minus 3.75 squared times the probability plus ... And if we were to do that for the next few, our variance of the random variable for passengers is 1.1875. There really isn't much of an interpretation for variance. It's just a measurement of spread. If you square root it, you get the standard deviation. And so the standard deviation of this random variable is 1.0897. So what this means is the number of passengers on a trip will typically differ from the mean by about 1.09 passengers. This is the typical deviation from that expected value. So not every single day are you going to get to the expected value of 3.75. Typically, you're going to be off by about 1.09 passengers, especially with standard deviation and means and expected value. Do not round them because they are talking about an average. And averages certainly can be decimals. Let's take a look at what happens if we consider that each passenger has to pay for this trip. Each passenger pays $150 to be on this tour. So how is this going to change our probability distribution? Well, now it's going to be, I'll say, money collected and then probability. And we'll take a look at our distribution now. Well, there's still 5 outcomes. You could have 2 passengers, and if they both pay $150, you just take 2 and times it by 150. So there is, the money collected for 2 passengers would be $300, and that still has a 15% chance. So that's not going to change the probability. So essentially what we're doing is we're multiplying by 150. And if we were to do that, we get $300, $450, $600, $750, then $900. All these probabilities are going to stay the same. Now, how is this going to change our distribution? How is this going to change, especially how will it change the expected value, and how will it change the standard deviation if we multiply all of these by 150? Let's take a look at Desmos. So here I have the distribution of passenger data. What we're going to do is take a look at how this distribution moves if I were to multiply everything by 150. So I have this little slider down here, and it's going to go up to 150 very slowly. We're going to see how this changes the expected value. So we expect on average about 3.75 passengers in the long run. However, if we change this into money collected, let's see how this distribution changes. So watch closely. Okay, that was very fast. So watch how this changes. There it goes. Oh, and it's off. Okay. So I'm slowly multiplying. So you should be asking yourself a few things. Is the expected value changing? Obviously, yes, the expected value is changing. Is the spread changing? Is the graph getting tighter or larger? Your answer should be yes. Look, it's getting wider as we're multiplying. The expected value, or the mean, is being shifted and being multiplied, but also the spread of the data is changing as well. It's getting wider as I'm multiplying. So now I've multiplied the data by about 77. We're almost at 100 here in a second or two. But when you multiply data, both the mean and the standard deviation are going to change. So let's multiply all the way up to 150. And we get this distribution here. Now notice, our old expected value was 3.75. Our new one is 562. Our old standard deviation was 1.08-ish, and now it's 162. So both of these have been multiplied by 150. If you multiply or divide a set of data, the mean and the standard deviation will both be multiplied by that number. So in this case here, this is our old expected value times 150. This is our old standard deviation times 150. Turns out, this is not just all the money that you are going to get. Sure, the people are going to pay $150 each. However, you have to pay for gas, you have to pay for other costs, you have to pay for the maintenance ship of the truck, you have to get it serviced maybe, it depends on the tour. But let's say that this happens. Let's say that this is the money that was collected. Okay, so we would expect to collect this amount of money. After many, many tours, we should expect to collect this amount of money per tour on average. But the tour costs you $100 each time you do it. So we have this distribution. What would happen if we subtracted $100? Not changing the units, we would just subtract 100. We are not multiplying, we're just gonna take away $100 for each tour. Well, watch closely, watch what happens if I want you to watch 2 things. Watch closely, I want you to watch if the mean changes and how it changes, and if the standard deviation changes and how it changes. So I'm gonna subtract $100 because it costs $100 each tour to just pay for maintenance, gas, so on and so forth. I'm gonna subtract $100 in 3, 2, 1. Okay. The expected value, did it change? Yes, it's now $100 less than it was. Standard deviation change? No. The typical deviation from the mean is not going to change. Just because you subtracted $100 to compensate for costs, that doesn't mean that the amount of money coming in is going to change on average. Addition or subtraction only changes the mean. It does not change the standard deviation of your random variable, of your probability distribution. Let's take a look at an example that would utilize transforming data. This one's titled The Baby in the Bathwater. Let's say that one brand of bathtub comes with a dial to set the water temperature. When the baby safe setting is selected and the bathtub is filled, the temperature X of the water follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. So this is the baby safe distribution of the temperature. So we're going to say that X is equal to temperature of water in the bathtub. We know that it's normally distributed. And it has a mean. It has a mean of 34 degrees Celsius and a standard deviation of 2. Okay, this is the baby safe distribution for the water temperature. Let's say that we wanted to convert it instead of degrees Celsius into degrees Fahrenheit. Let's define the random variable y as the temperature of the water in Fahrenheit. And that transformation looks like this. It's 9/5 Celsius plus 32. So this is the original distribution, 34. This is what the distribution would look like in Celsius. And we need to consider how would this distribution change if we converted it into Fahrenheit. Well, a few things. The old distribution had a mean of 34, standard deviation of 2. So this multiplication, so we're going to take our Celsius distribution, and the first thing we're going to do, order of operations, the first thing we're going to do is multiply by 9/5. Recall that if we're multiplying or dividing, it changes both. Remember how the graph kind of moved and got wider. So if we multiply by 9/5, we are going to get a new mean and a new, so this is going to change, the 9/5 will change the mean and the standard deviation. This is just going to change the mean. Remember that the 32 is just going to shift it up. It's not going to change the spread. It would just shift up like this. So the 32 is not going to change the standard deviation. So the new mu of y is going to be 34 times 9/5, and then the mean will be added. The mean is going to be, so the mean will be affected by this 32. So our new mean is going to be 93.2 degrees Fahrenheit. The standard deviation of y will only be affected by the 9/5. So the standard deviation was 2, and now since we're multiplying, this 2 is only going to be affected by the 9/5. The 2 will not be affected by adding 32. That's just a shift. So the new standard deviation is going to be 3.6 degrees Fahrenheit. That means that we'd have a new distribution. So our distribution is going to be slightly different now. We're going to have a normal distribution with a mean of 93.2 and a standard deviation of 3.6. So our new distribution would look something like this, and this is now in degrees Fahrenheit. According to Babies R Us, the temperature of a baby's bathwater should be between 90 degrees Fahrenheit and 100 degrees Fahrenheit. Find the probability that the water temperature on a randomly selected day when the baby safe setting is used meets the Babies R Us recommendation. So this is asking, what is the probability that on a randomly selected day, remember y is now this transformed data, that the temperature is below 100 but above 90. So here's 100-ish, here, 100, and then here is 90-ish. We want to find this probability right here. This is very similar to an example that we saw previously. So what we're going to do is we're going to take and find the z-score for 90. So it's distance away from the mean, divided into chunks of standard deviations. And this is going to have a z-score of negative 0.89. And this is going to have a z-score. So it's distance away from the mean, divided into chunks of standard deviations. Notice how it's 1 and like more than half, so we get 1.89. And then we look both of these up in our z-table. So negative 0.89, so negative 0.8. I'll go over to 9, the very last one. So 18.67, and that's this. This area here is 18%-ish. And then if we look up 1.89, it's 0.9706. 0.9706, that's all of this area, right? This is 0.9706 is all of this. So it's too much because we just want this area here. So if we look up the percentile, if we look up this percentile, if we look at the percent below this, it's going to give us everything. So we need to remove this area here. So we take the larger percent and then we subtract the smaller percent from that. And we get our probability. So it looks like there's about a 78% chance that the water temperature meets the recommendation on a randomly selected day. I don't know about you, but like it's below an 80% chance that your baby's going to be put in a safe temperature. I don't know. I think they should update that temperature setting. That seems a little bit low for that seems a little bit low for standards. But anywho, there's about a 78% chance that on a randomly selected day, the water temperature of the baby safe option will be within the Babies R Us recommendation. Okay, so that was kind of a quick one. A lot of similar ideas that we saw in the past. This is kind of a nice chapter to kind of end on because it's reviewing a little bit on probability, normal calculations, whatnot. So your suggested practice, this is 6.2, day 3. Your suggested practice is the following. I suggest that you practice 27 to 30, 35, 37, 39 to 41, and 43 and 45. I'm playing around with using software to hopefully do a live chat. I would really enjoy doing that with you folks so we can ask questions on suggested practice as we start reviewing. Remember that we're going to get updates from the College Board a little bit later. So yeah, I suggest that you practice this. Please, on the comment thread of this video, post questions that you have either regarding the examples in the video or questions from your suggested practice. There is also a bunch of Khan Academies. I've noticed that folks have been doing their Khan Academies, which is great, but there's a lot of practice there. Keep a look. It continues on for a while, so I assigned all of random variable units. So just because it's on the first page, there's like I think an overload. Anyway, take a look, make sure that you look at all the pages in your assigned practice. Have a good rest of your day, stay safe, wash your hands. This has been Math Think.